everybody. So the final topic that I'd like to go over is the fast Fourier transform. So in the previous class we talked about using DFT to calculate the convolution. If you remember the last example that we've done, we said we can use the discrete Fourier transform to do the calculation of the convolution, and we've done the MATLAB example. And we said that the reason we're doing this is because we can calculate the discrete Fourier transform very efficiently. So we're going to look today at how is the discrete Fourier transform calculated efficiently, and it is done through the fast Fourier transform. Okay, so if you look at the implementation of the discrete Fourier transform, if you look at the discrete Fourier transform pairs, x of k, summation, x of n 1 over n, the summation, x of k. If you look at the computational complexity, each x of a calculated for each value of k, we're going to need n complex multiplication, multiplying x of n with the exponential. And also, we're going to need n minus 1 complex additions. We're going to have to add all these terms to calculate each value of x of k. Now, we have to calculate for n different values of k. K goes from 0 to n minus 1. We have n values. So therefore, the total number of complex multiplications is n squared. And the total number of complex additions is going to equal n multiplied by n minus 1, which is approximately equal to n squared. Now also, if we look at the complex additions, we're adding two components together, the real part, imaginary part, so it is equivalent to two real additions. And if you look at the complex multiplications, if we have two complex numbers, we're multiplying together, a plus jb, c plus jd, we're going to have to multiply AC, BD, we're going to multiply BC, AD. So therefore, one complex multiplication is equal to 4 real multiplications plus 2 real additions. So, and of course, the same thing applies for the inverse discrete Fourier transform. It's going to require the same number of multiplications. So to summarize everything, the n-point discrete Fourier transform requires n squared complex multiplications, n multiplied by n minus 1 complex additions, and if you look at the real multiplications, is going to equal to 4 multiplied by n squared, and 4n squared minus 2 multiplied by n real additions. Okay, so if we look at the calculation of FFT, if n is very large, which usually the case, then the number of computations that is required is very, very large. And therefore, we need a more efficient method to perform the discrete Fourier transform. And this efficient methods of calculating the discrete Fourier transform, we refer to it as fast Fourier transform. So this is the general term that refers to a large class of efficient algorithms for the evaluation of the discrete Fourier transform. Now what we're going to do in this lecture, we're going to look at one of the algorithms, which is the decimation in the time domain. We can do also decimation in the frequency domain. However, we're going to do it in the time domain, and hopefully that will give you an idea of how the discrete Fourier transform is calculated very efficiently using the fast Fourier transform. Okay, so before we start, let's just do some simplifications. We're going to define the twiddle factor before, exponential of e to negative j multiplied by 2 pi divided by n, and therefore we can write x of k, the discrete Fourier transform, as the summation of x of n multiplied by w sub n to the power of k sub n. W sub n refers to the exponential of negative j 2 pi divided by n, so nothing changed. At the same time, we can calculate also x of n is going to equal 1 over n, summation x of k multiplied by wn to the power of negative k multiplied by n. Okay, so let's look at some properties of the twiddle factor wn that we're going to be needing in our lecture today. So the first one, wn to the power of k multiplied by n minus n, is equal to wn to the power of negative k multiplied by n, which is equal to wn to the power of kn over all conjugate. And of course, it is easy to show any one of these. If you look at the print here in blue, wn to the power of k multiplied by n minus n is equal to the exponential e to negative j 2 pi k multiplied by n minus n divided by n. We can simplify this. This is going to equal e to negative j 2 pi multiplied by k. N with n is going to cancel. And then we're going to have another term that is going to be positive j 2 pi multiplied by n multiplied by k divided by n. Now this first term is going to just equal to a 1 because we multiplying 2 pi exponential to the j 2 pi by an integer. The second term is going to equal e to j 2 pi n multiplied by k divided by n. And if we look at how we define the twiddle factor, we can write this as w to the n, or sub n, to the power of negative k multiplied by n. So if we take w sub n and take it to the power of negative k to the power k multiplied by n, the negative is going to cancel, and I'm going to get j 2 pi multiplied by n multiplied by k divided by capital N. Okay, so we can show all of these properties of w of n. If I look at w sub n to the power of k to the multiplied by n, this is going to equal to a 1 because I'm going to be getting, if I look at the twiddle factor, I'm going to be multiplied by k multiplied by n. I'm going to get e to negative j 2 pi multiplied by an integer, which is going to equal to a 1. W sub n to the power of n over 2, I'm going to get e to negative j pi multiplied by an integer, and therefore that is going to equal negative 1. W sub n to the power of kn is going to equal w sub n k multiplied by n plus n, which is going to equal wn k plus n multiplied by n, which means that the w sub n is periodic, w sub n to the power of kn is periodic in n and k. If I add an n, I'm going to get the same thing as w sub n to the kn. If I add a small n, I'm going to get also the same value of w sub n to the kn. Finally, w sub n to the power of 2kn is the same as w n over 2 to the power of kn. So here, if I divide this by 2, the 2 is going to go to the numerator, and therefore is going to give me the same as w of n to the twice of k multiplied by n. W sub n over 2 to the power of kn is going to equal w sub n to the power of 2kn. Okay, so let's look at how we're going to make the discrete Fourier transform calculation efficient. We're going to do decimation in the time domain. And what we're going to be doing, we're going to be taking the calculation of n-point discrete Fourier transform, and we're going to be breaking it into smaller pieces. We're going to be breaking it into 2 n over 2 point discrete Fourier transform, which in turn can be broken into 4 n over 4 point discrete Fourier transform. Now, why will we be doing this? As we will see, because the computation complexity is directly proportional to n squared. So therefore, if I break the discrete Fourier transform into a smaller n, the calculation will be much more efficient. Now what we're going to see is how we're going to break the discrete Fourier transform into a 2 n over 2 point discrete Fourier transform. So let's look here. So first thing, we're going to assume that n is of power of 2. So we have n equal 2 to the power of v. I want to calculate x of k, summation x of n, w to the nk. And what we're going to do is we're going to break this x of k into an even part and odd part. So I'm going to look at the summation. I'm going to look at the summation from 0 to n minus 1. I'm going to break it into an even and an odd part. The even part is going to go from 0 to n minus 2, x of n, wn to the power of nk, plus the summation from n to n minus 1, x of n, w of n to the power of nk. Remember, n is going to be integer, so n minus 1 is going to be an odd number. N is even, so n minus 1 is going to be an odd. Okay, so till now we didn't do anything. We just took this summation, we broke it into two pieces, even and odd. Now what I'm going to do is we're going to replace n with 2 multiplied by r, since it's an even number. We're going to replace n by 2r plus 1 for the odd part. So for the even part, we're going to replace n with 2r. For the odd part of the summation, we're going to replace it with 2r plus 1. So therefore, this summation, we can write it as the summation from r equals 0 to n over 2 minus 1. And instead of n, we're going to have x of 2r, wn to the power of 2r multiplied by k. Again, I replaced n with 2 multiplied by r. And the odd part is going to be the summation from 0 to n over 2 minus 1, x of 2r plus 1, w sub n to the power of 2r plus 1. Okay. Okay, so we can simplify. If I look at the term for the odd, I can write w sub n to the 2r plus 1 multiplied by k as w sub n multiplied by k. So this part here, and I can take it outside the summation since it doesn't have an r in it. And w sub n to the power of 2r, I can write it as w sub n over 2 to the power of r multiplied by k. Again, as we've seen in the properties, w sub n over 2 to the power of r multiplied by k is the same as w sub n to the power of 2 multiplied by r multiplied by k. Okay, so continuing, if I look at the first summation, this is nothing other than n over 2 point discrete Fourier transform, because we're only taking the even part. And the second part is going to be n over 2 point discrete Fourier transform that we're going to call h of k, and the first part we're going to call it g of k. So therefore, x of k, we can write it as g of k, which is the first summation, plus w to the power of k multiplied by h of k, which is the second summation. And we're going to use this formula to calculate x of k for k between 0 and n minus 1. So the first half of x of k calculations, we're going to use this formula to calculate. However, this will give me half of the discrete Fourier transform. I still need x of k for n greater than, for k greater than n over 2 all the way to n minus 1, the second half of the k values for x of k. So let's see how we're going to calculate that. Since w to the sub n over 2 to the power of r of k plus n over 2 is equal to w to the power of r multiplied by k, and this is the property, the third property of the properties of the w, then if I look at g of k plus n over 2, this is going to equal to g of k. So if I look at this summation here, if I add n over 2 to k, I'm going to get, if I look here, x of k equal g of k, this is g of k. G of k, if I add to k n plus 2, I'm going to still get the same as g of k. If I look at h of k plus n over 2, I'm going to get the same as h of k. Okay. Now, if I calculate x of k plus n over 2, I'm getting the same g of k, the same h of k. The only thing that is going to change is this twiddle factor, w sub n, is going to have k plus n over 2. So the x of k plus n over 2 is going to equal to g of k plus w sub n to k plus n over 2 multiplied by h of k. Now we can take this wn to the power of k plus n over 2 and write it as wn to the k multiplied by wn to the power of n over 2. Or we can write it also as g of k minus wn multiplied by h of k, and this is for k between 0 and n minus 1, which is the second half of x of k. Okay. So continuing, if we want to compute the endpoint DFT, I'm going to get, and I'm sorry, there is a k missing here. Yeah, wn to the k, and wn to the power n over 2 is going to equal negative 1. Okay, so if we put everything together, we took the DFT, we broke it into 2-point DFT, and according to the formula that we just had, we're going to take x0 to x0, x of 2, x of 4, x of 6, the even part, and we're going to take the odd part. We're going to calculate g of 0, g of 1, g of 2, g of 3. We're going to calculate h of 0, h of 1, h of 2, h of 3. And then we're going to use the calculated g0 through g3, h of 0 to h of 3 to calculate x of 0, x of 1, all the way to x of 7. However, we're going to be calculating x of 0 to x of 4 using the g's and h, and at the same time we're going to be calculating x of 4 to x of 7, and in this case we're assuming we have 8-point DFT. As you can see, once we calculated the g's and h, we can just calculate x of 0 from g of 0 plus h of 0 multiplied by w sub n to the 0. We can calculate x of 1, for instance, is equal to g of 1 plus this path here, h of 1 multiplied by w sub n to the 1, and so on. If we calculate x of 4, let's highlight how we're calculating it. X of 4 is going to equal to g of 0 plus h of 0 multiplied by w sub n to the power of 4. Okay, so again, this is a direct implementation of the equation that we had in the previous page. So this is the result of the first decimation. And if I look at the computation complexity, I have 2 multiplied by n over 2. So since I have n over 2 DFT, I'm going to have n over 2 squared, and I'm going to have multiplied by 2 because I have the even and the odd. And then I'm going to have n for the multiplication of h by the twiddle factor. So all these multiplications that I'm multiplying is going to result in n also multiplication. So the overall is going to 2 multiplied by n over 2 squared plus n. And if I look at the complex additions, I'm going to get 2 multiplied by n over 2 squared plus n, which is due to the summation of g of k and h of k. So at each point here, I'm adding these two terms together, and therefore I need n summations over O. So there's an n summations that is added to the overall cost of the computation. Now we can see already for n that is larger than 2, this is going to be less than the original number of computation. So because we are squaring the value of n, the smaller the value of n that we're squaring is going to result in saving in the computation. Now we can continue this process by breaking the computation of g of k and h of k into n over 4 point dft. Of course, assuming n over 2 is even, which is the case since we have we assumed n is equal to the power of v. So in this case, I'm going to now break g of k into an even and odd. So g of k was equal to the summation from r equal to 0, n over 2 minus 1, g of r, w n over 2 to the power of rk, which we can write it as the summation from 0 to n over 4, g of 2l, w n over 2 to the power of 2lk, plus the summation of the g of 2l plus 1, wn over 2 to the power of 2l plus 1 multiplied by k. So similar to what we've done with the calculation of n over 2, we can do exactly the same with the g of k calculations. So then we can rewrite this as equal to the summation of g of 2l wn over 4 to the power of l k. This 2 and 2 I can write it as n over 4. So this is nothing other than the n over 4 point dft. And then I have also the second term is going to be the n over 4 point dft. And I'm going to do similar to what we've done with the n over 2. I'm going to take the twiddle factor wn over 2 multiplied by k outside. So we have this multiplying by the summation of g of 2l plus 1. We can do similar thing to h of k. We can break it into even and odd terms, and we're going to get this summation here. Okay. So therefore, if I look at the calculation now, after the second decimation, so this is after second decimation, is going to look something like we have here. I'm going to be calculating the n over 4 point dft, and I'm going to be calculating g of 0 all the way to g of 3 here, and h of 0 all the way to h of 3 here. And then from the g and h I can calculate x of 0 to from 0 all the way to 7. And again, here we're assuming n is equal to 8 to show the calculations. Okay, so if I look at the complex multiplications and additions that we have here, I'm going to have 2 multiplied by 2 multiplied by n over 4 squared plus n over 2 plus n, which we can write as equal to 4 multiplied by n over 4 squared plus 2 multiplied by n. Okay. So continuing in this fashion, the number of complex multiplication additions after the rth decimation is going to be given by 2 to the r multiplied by the number of multiplication needed for an n over 2 to the r point dft plus r multiplied by n. So therefore, if n is equal to the v, then the discrete Fourier transform can be halved v minus 1 times. So again, if v, for instance, is equal to a 3, then we can do the halving 2 times, finishing with a bunch of 2-point discrete Fourier transform. So again, if v is equal to 3, we can half it. We're going to get n over 2, which is going to be 4-point DFT. Then we can half it. We're going to get 2-point DFT. So the first stage is going to be a 2-point discrete Fourier transform that is given by y of 0. These are the input, y of 0, y of 1. And we're going to be calculating y of 0 plus y of 1 on one output, and the second output y of 1, which is going to equal to y of 0 minus y of 1. Okay. And just to the notation, just to make it clear, these are small letter. I have them as capital letter, which is not right. So the input is small letter, y of 0, y of 1, and the output is capital letter that is calculated. Y of 0 is going to equal to y of 0 plus y of 1, since wn to the 0 is going to equal to a 1, and w of 1 is going to equal to y of 0 plus w of 1 multiplied by w sub n to the power of n over 2, which is equal to negative 1. So it's going to equal y of 0 minus y of 1. So if you look at this, technically a 2-point discrete Fourier transform requires 0 multiplications, because the Twiddle factor is going to equal 1 and negative 1. So we do not need to multiply, we only need to do addition. One addition, second addition. Of course, subtraction is considered addition. However, for symmetry, we're going to say that we're going to need 2 multiplication, which is the multiplication of the Twiddle factor wn0 and w sub n to the power of n over 2. And we're going to need two additions. So we're going to be adding these 2 terms together here. And we're going to be adding the 2 terms together here. So therefore, the number of complex multiplication additions needed to perform an n equal to v point discrete Fourier transform using the decimation in the time is going to equal to 2 to the power v multiplied by 2 plus v minus 1 multiplied by n. Again, for instance, if 2 to the power v is equal to 8, then 2 to the power v minus 1 is going to equal to a 4 multiplied by 2 plus 2 multiplied by 8. 2 is for the first block, because we're going to be calculating 2-point DFT is going to need 2, and then we're going to have 4 of them, so 4 multiplied by 2 plus 2 stages multiplied by 8 of the multiplications of the Twiddle factors. We can simplify this. If we add the terms, this is going to equal to v multiplied by n, which is equal to n multiplied by log 2 of n. So let's see how this looks like. So this is if we have 3 stages for the calculation of the discrete, 3 stages for the calculation of 8-point DFT. We have log 2 n stages, so in this case we're going to have 3, and we're going to need n multiplications per stage, and therefore this is going to equal to n multiplied by log 2. of n. Okay. And hopefully this is clear. You can see 3 stages. We need n multiplications, 1, 2, 3, 4, 5, 6, 7, 8. Another 8 multiplications. Another 8 multiplications. So 8 multiplied by the 3 stages. And if we calculate the saving that results from this decimation, it will become apparent if we take n that is very large. So if we take n equal, for instance, to 10 to the power of 24, then for direct discrete Fourier transform, we're going to need n squared, which is going to require approximately 1 million multiplications. However, if we do decimation in the time domain, then it's going to require n log 2n, which is going to be 10,000. So therefore, you can see the saving that we got by doing the decimation. We went from 1 million to 10,000 multiplications. Now we can also reduce this even further, because if I look at the number of multiplications, we can reduce it even by half using additional symmetry as follows. In any given stage, we have the computation that is going to look something like this. We're going to have an input, a small letter x, and a small letter x sub m at p and x sub m at q. And we're going to be calculating capital X sub m plus 1 at p and capital X sub m plus 1 at q. And this is what the butterfly configuration look like. However, if we look at this calculation, w sub n to the r plus n over 2, we can write it as w sub n to the r multiplied by w sub n to n over 2. This is going to equal to -1. So this is going to equal negative w to the power of n to the r. So therefore, we can reduce this as follows. Since we're going to be multiplying both terms by wn to the r, we can multiply first by w. If you look here, multiply first by wn to the r, and then just add the 2 terms together here and add the 2 terms together here. So basically, we're going to take x of m, x sub m at q, and I'm just going to multiply it directly here instead of having to multiply it twice. Instead of multiplying it here and here, I can just multiply it once and then just add the results at the output. Okay. So therefore, each butterfly is going to have 1 complex multiplication instead of 2. This is the only multiplication we're going to do with this twiddle factor. And therefore, the total number of complex multiplication is going to be given by log 2 n stages multiplied by n over 2 butterflies per stage multiplied by 1 multiplication per butterfly. And therefore, the total cost of the calculation is going to be n over 2 multiplied by log 2 of n. Okay. One final observation that we're going to make is that when we do the calculations, we scramble the input data. The order of the input data gets scrambled because each stage requires data to be separated into even and odd. So therefore, if I look at the calculation, I have x of 0, x of 4, x of 2, x of 6, 1, 5, 3, 7. I have the even together and have odd together. So therefore, keep in mind that at the input, we have to scramble the data at the input of the calculations. Now, to determine the correct order of the calculations, we can just take the index of the input and we're gonna reverse it. So to determine the order, so for instance, if I have x of 0 at the input and x of 1, x of 2, x of 3, etc. So this index n is 0, 1, 2, and 3. We're going to take index n in binary. So this is going to be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Then what I'm going to do, I'm going to take this index, I'm going to do bit reversal. So since this is 0, 0, 0, nothing's going to change. Here is going to become 1, 0, 0. Here is going to be 0, 1, 0. 0, 1, 1 is going to be 1, 1, 0. And therefore, the new index, if we like, call it n prime, this is going to be 0. This is going to be 4. This is going to be a 2. And this is going to be a 6. So therefore, this is the order that we're going to have the data entered. Okay, so this hopefully will give you an idea of how the FFT is calculated very efficiently by using these algorithms that will take advantage of not repeating the same calculations and doing the calculation more efficient. Now we showed you how to do this decimation in the time domain. We could have also done the same thing in the frequency domain and even reduce the complexity or the cost of doing this calculation. Thank you, everybody. If you have any questions, please let me know, email me. And remember, the project I think is due tomorrow, so please make sure you turn it in. And best wishes to all. Thank you all.